So section 10.2, we're going to expand our horizons. We're no longer looking at the solution of 2 equations and 2 unknowns. We're looking at the solution of 3 equations and 3 unknowns. So what's called a 3 by 3 system of equations. Now, the geometry gets a lot more intense in something like this. And let's see, I'm not seeing a picture of it, but for those of you at home, you're going to have a little tougher time imagining this. Instead of looking for where 2 lines intersect, we need to figure out where 3 planes intersect. So let me see if I can. One more attempt at finding this. Planes. Yeah, here we go. So here's some of the things that can happen. Now on the right here, this is what we want to happen. We want 3 planes to intersect at a point. So if you're using the room that you're in, you could think of the front wall, the right wall, and the ceiling all meet at a corner, right? That's what we're looking for. This, by the way, is why we can't do this kind of stuff in decimals. Decimals can only do 2 by 2 systems of equations, so you're stuck. But there's other things that can happen. You could have 3 planes that meet along a line, like right here. So there's an infinite number of solutions here. But how about over here? Is there a point that's in common to all 3 of these? No. Likewise here and likewise here. So the number of solutions that you get when you're solving a 3 by 3 system of equations is, in some sense, what you would see if you're solving a 2 by 2 system. You could have 0, 1, or infinitely many solutions. It's just going to depend on the nature of the equations. So let's take a look at this first one. And this is just kind of building up skills in order to solve your 3 by 3 system of equations. So it says, you've got this 3 by 3 system of equations, add 1 times row 1 to row 2. Okay, well, let's practice that. So I like to write 1 times row 1 plus row 2. Above this, so I kind of remember what I've got going. 1 times row 1 is x minus y plus z equals 1. Added to row 2 is x plus 4y plus z equals -1. And the nice thing that happens here is that the x's cancel out. So I'm left with 3y plus 2z equals 0. And that's it. That's the first thing that I asked you to do. And I kind of asked you to do that again, except this time I want you to add 3 times row 1, excuse me, -3 times row 1 to row 2. So let's do that. Put a little bar here to keep these clear, but they're separate. So -3 times row 1 added to row 2. Let's see how that would look. That's going to be -3x plus 3y minus 3z equals -3. Added to row 3, I wrote row 2. 3x plus y minus 2z equals 2. And again, I'm getting rid of that leading term of an x. 4y minus 5z equals -1. That's all you're asked to do here in these first 2, is just get rid of the x's. Now, there's a nice reason to practice that kind of skill, and that is, if we did one more manipulation to our system of equations, then we could get it to look like we have in example B. So in example B, you're given this triangular system of equations. It's called triangular because on the left-hand side of our equations, well, the shape of this system of equations looks kind of like a triangle. It is. So it's a upper triangular system. Now, if you're asked to solve this, well, I already know what z is, right? Z is -3. But knowing z is -3, I can put that into the second equation. Y minus -3 equals 5. So if I put in -3 here for my z, that becomes y plus 3 equals 5, or y equals 2. Hey, look at that. 2 down, 1 to go. Now for that last one, I need to go up to the first equation, because the first equation has an x in it. And I need to have an x in this equation if I want to solve for x. So it's going to be x minus 5y plus z equals 0. So let's put that in there and see if we can't solve. So I'm going to put in the 2 for y and the -3 for z. And let's see how that works out. That's going to be x minus 10 minus 3 equals 0. So x minus 13 equals 0. Or in other words, x equals 13. Yay! Now, as far as writing your solution in WebAssign is concerned, the way you write your solutions in WebAssign for something like this is no longer an ordered pair. You have 3 variables. Now, you don't really have to know these names, but sometimes I call this a 3-tuple or an ordered triple, whatever you want to call it. It's always going to be in alphabetical order. So if your problem is A, B, and C, or P, Q, and R, you know, these letters are going to be in alphabetical order as you write them here. So for WebAssign, you should type in 13, 2, and -3. That would be your answer in WebAssign. Yay. Now, you don't always just have to use the first row and the first variable. You can do other things. So if you're to use the first row to try and eliminate the x here, that'd be a lot of work. You'd have to multiply, say, the top row by 1/5, and you get all those fractions, and then add it to this one. Yuck. So how about a different way to eliminate this negative x term? Can anyone see something that they would suggest? What do you have to add to negative x to make it equal to 0?
X.
Positive x. There's a positive x right down there. So I would just suggest 1 times row 3 added to row 2. So 1 times row 3, well, that's just going to be row 3. And then add to row 2. And I end up with -6y plus 6z equals -6. Hey, that's all you're asked to do. Okay, so we've practiced things a couple times. Let me show you one from beginning to end. And maybe you just kind of want to relax if you're taking notes at the moment, and just watch this one, because it's going to go a little bit fast. And unless you printed out this ahead of time, then it makes it a little bit harder to keep up. But let's take a quick look at this one. So this is our 3x3 system equations that we're going to start out with. And what I'm going to do is I'm going to use one of these equations to eliminate a variable from the other 2. Now, you don't have to always eliminate the first one, the x. You can eliminate any variable. So what you should look for are things that have a coefficient of 1 or -1. In this case, the first equation has a coefficient of 1 for the y. So I'm going to choose that one. And notice I'm circling it because I'm going to use that equation twice. I'm first going to eliminate the y from this equation, and then I'm going to use this equation again to eliminate the y from this equation. So let's see what that looks like. So to get rid of the y down here, what would I multiply this by? Well, I could do -2 times this row, -2 times row 1, added to row 2. And that would look like -4x minus 2y minus 8z equals -24. And add that to x plus 2y plus 2z equals 9. Now that y variable is going to drop out, and that's okay. It's going to give me -3x minus 6z equals -15. And just leave it. All right? We're going to leave that there until we get rid of the y from this equation. Now how am I going to get rid of the y here? Well, what I multiplied this by to add down to this equation. So that would be a 3. So 3 times this row added to this row. Let me squeeze it in here. 3 times row 1 added to row 3 is going to look like this. 6x plus 3y plus 12z equals 36. And then added to 3x minus 3y minus 2z equals 1. And that'll end up giving me 9x plus 10z equals 37. So I did that twice. Now the nice thing about what we just did, this equation is right here. And this one is right here. I've got a new system of equations. It's an equivalent system of equations. Its solution is the same as our original system of equations. So this thing that I'm circling in yellow, this has the same solution. But the nice thing about it is that these two equations have just two unknowns. So I'm going to focus in on those two equations. And I kind of brought them over here. All right. So nice. Those two equations have two unknowns. You can solve this any way you want now. You can solve it by graphing. You can solve it by substitution. You can solve it by addition, Kramer's rule, iterative methods. There's dozens of ways you can solve this. Now, for us, probably the easiest thing to do would notice that, gee, if I multiply the top equation by 3, I can get rid of this 9x. So 3 times the top equation gives me this. When I add these two together, I end up with -8z equals -8. Nice. So then what? If -8z equals 8, what does z equal? All right. I'll assume that it's in the chat, but z equals 1. So there you go. Z equals 1. That's 1/3 of our solutions. I need to know what z is. I need to know what x is. I need to know what y is. But for right now, now that I know what z is, I can go back into one of these equations and solve for x. So I think I like this one better because it's got all positive numbers. So it's going to be 9x plus 10 times 1 equals 27. I'll subtract 10 from both sides. 9x equals, should have been 37, my bad. Now I get the 27 that I wanted. X equals 3. So 2 down. X equals 3, z equals 1. Now that I've solved for those two, I've got to go back to one of the other equations and finish solving, this time for y. Now you can pick any equation here that you find convenient. I just chose the top one, just out of being systematic maybe, I guess. But I'll plug in the 3 for the x and the 1 for the z and get 6 plus y plus 4 equals 12. So y plus 10 equals 12, or y equals 2. And that's the third part of your solution. Now on a test, you can get away with just circling all 3 parts of your solution. That's fine. On WebAssign, you're going to have to type it in as 3, 2, 1, like this, an ordered triple. So that's what they're going to expect. Overall, your steps to solve a system of equations, in general, a 3 by 3 system of equations, are going to be just what we did here. You're going to pick one of the equations and use it to eliminate a variable from the other 2 equations. So that's what we did here. We got rid of the y from those 2 equations. Once we did that, then we're going to solve the other 2 equations for the remaining 2 unknowns. So that gave us a 2 by 2 system. We solved those 2 equations and 2 unknowns for z and x. And once we knew what z and x were, then you go back and you substitute in and solve for the remaining unknown. So we did that here. We solved for the remaining unknown. So there you go. There's your 3 by 3 system of equations. All right. Let's do a few examples here. A few more examples. And what I want to show you is a couple things that can happen, and also some ways you can be a little bit more clever about your work so that maybe you don't have to do as much work. So let's start with let's see. Example D, which is x plus y plus z equals 0, and negative x plus 2y plus 5z equals 3. And finally, 3x minus y equals 6. Whew. Okay. Now, this one's a pretty cake system of equations to solve. It is so because you've got a lot of variables that have a coefficient of 1 or negative 1. So for instance, it'd be easy to use the middle equation to get rid of this x here and this x here, or use the y here, get rid of the y's or the z, etc. But one equation stands out as being the best one to use. And what I want you to notice is that that third equation doesn't have a z in it, does it? It's just 3x minus y. That's actually a helpful thing. It means we have to do less work. So let me show you. We need to get rid of the z from one more equation. So I'm going to multiply the top equation by negative 5 and get rid of the z here. So negative 5 times row 1 added to row 3, no, added to row 2, I should say. So negative 5x minus 5y minus 5z equals 0, added to negative x plus 2y plus 5z equals 3. All right. When I do that, I end up with negative 6x minus 3y equals 3. Now, why is that special? What's nice about it is it just depends on x and z, right? Is there another equation that just depends on x and z? Yeah. It's right here. Unlike our last example, I didn't have to do this twice. Most of the time, you're going to have to do this kind of step twice because you won't have an equation that already has a missing variable. But we're in good shape in this one. So here's my two equations and two unknowns. I got 3x minus y equals 6, and negative 6x minus 3y equals 3. All right, well, how do you want to solve this one? You could solve it by substitution. Let's do that just to practice substitution. The reason I suggest substitution is that it's easy to get y by itself up here. So if I move the y to the right-hand side and the 6 to the left-hand side, I get 3x minus 6 equals y. And now I can take that expression for y and plug it in here. Let's see what happens when I do that. So when you get here, you can solve any way you want. You could actually graph it. Nothing wrong with that. Negative 6x minus 3 times 3x minus 6 equals 3. So negative 6x minus 9x plus 18 equals 3. I get negative 15x equals negative 15. So wow, did a lot of work just to find out that x equals 1. That's okay. The nice thing about the substitution method here anyways is that it makes it easy to solve for y, or the other variable, whatever it may be in your case. I just plug it back in here. 3 times 1 minus 6 equals y. So negative 3 equals y. 2 down, 1 to go. So now that I've got x and y, I got to go back and find z. And I would pick any equation that looks convenient and find z. Now, how come I can't use the third equation to find z?
There's no z.
Yeah, there's no z there. So you have to use one of the first two. And the first one looks the easiest. So substitute x equal 1 and y equal negative 3 into x plus y plus z equals 0. So it's going to look like this. 1 plus y, 1 plus negative 3 plus z equals 0. Gives me negative 2 plus z equals 0, or z equals positive 2. Oops, spilled off the board a little bit there. There you go. Here's a little throwback question for you. Would you say the system of equations is consistent or inconsistent? Consistent, yeah. We found a solution, so it's consistent. Now, it would be dependent if we had an infinite number of solutions, but that's not the case for us in this one. So to kind of recap, usually when you're doing these things, you have to eliminate a variable from two equations. Like here, I eliminated the y from both of these, and then I had a 2 by 2 system of equations that I could solve. But because we were clever, because there was a z missing here already, we just said, all right, that'll be one of our equations, and we came up with another equation that didn't depend on z. We were able to solve that 2 by 2 system of equations for x and for y. Once you had those, we went back and substituted into the original equation to get z. Nice, 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 nice. Of course, it doesn't always stay nice. Let's take a look at some more examples. So let's see here. Example F. And yes, I am skipping example D. So x plus 2y minus z equals 15. 2x plus 3y minus 4z equals 31. And 3x plus 6y minus 3z equals 46. So you've got your choice of what variable you want to eliminate. Now, in our case, the only equation that has a coefficient, or that has variables with coefficients of 1 or -1, is the first one. So we could use the first equation to get rid of the x's here or the z's here. Doesn't matter which one you do. Part of me feels that, gee, we should probably eliminate the z just for variety and just to show you something else. But it's going to mean slightly bigger numbers. It's up to you. Want to get rid of the x's or the z's? Sam? X's? All right, we'll go with the x's. So to get rid of the x here, I want to multiply the first equation by negative 2 times row 1 added to row 2. So it's going to be negative 2x minus 4y plus 2z equals negative 30. Add that to 2x plus 3y minus 4z equals 31. The x's drop out. That's what's supposed to happen. Negative y minus 2z equals 1. Okay. Looking good there. Now I got to do that again and get rid of the x from the third equation. So let me do that here. This time I'm going to multiply by negative 3. Negative 3 times row 1 added to row 3. That's going to give me negative 3x minus 6y plus 3z equals negative 45. Added to 3x plus 6y minus 3z equals 46. And something's screwy going on here, right? What do I get when I add these together?
Cancel that. You get 0 equals negative.
0 equals 1. But 0 doesn't equal 1. So that's telling you something. What do you think is going on here? No solution. Now, without a lot more work, it's kind of hard to tell exactly what's going on, usually. But it's one of these situations here, that there's no point in common to all three planes. That's it. Now, if things had turned out different, we could get this kind of thing, but that's not what happened here. It's one of these. There's just no solution. Here, there's an infinite number of solutions, so look out for something different. So no solution. That would be inconsistent. So you're done. That's it. That's all there is on that one. So I could ask you on an exam, show me that this is inconsistent, for instance. Okay, let's try example G. Example G. This time we've got x plus y minus z equals 0, and x plus 2y minus 3z equals negative 1, and 2x plus 3y minus 4z equals negative 1. All right. This time, let's do something different. Let's either eliminate the y's or the z's. I mean, the first equation still works out good for us because all three of these have a coefficient of 1 or negative 1. But let's eliminate something different just for giggles. What would that be? What do you want to get rid of? The y's or the z's? Your choice. Y or z? Get rid of the y. All right. So we'll go with the y's. Now, if I'm going to get rid of the y here, what would I multiply the first equation by? Negative 2. So negative 2 times row 1 added to row 2 is negative 2x minus 2y plus 2z equals 0. I'm going to add that to x plus 2y minus 3z equals negative 1. And I'll end up with negative x minus z equals negative 1. And just leave it there. Work on the next one. Okay, so for the next one, if I'm going to get rid of the y from the third equation, what am I going to multiply the top row by? Negative 3. So negative 3 times row 1 added to row 3. It's going to look like this. Negative 3x minus 3y plus 3z equals 0. 2x plus 3y minus 4z equals negative 1. And when I add here, I get negative x minus z equals negative 1. Okay. So I got my two equations and two unknowns. So let me put those together. The first equation, coming from here, is negative x minus z equals negative 1. So that's that equation. And then I got this equation, which is negative x minus z equals negative 1. And if you're looking at that going, wait a minute, something looks a little weird, you're right. What do you notice about these two equations? They're the same. So if you tried to solve, you really couldn't. Your solution is the whole line. It's not just one point, it's everything. These in effect intersect along a whole line. If you try to solve this, say by the addition method, multiply the top row by negative 1, you get x plus z equals 1. added to negative x minus z equals negative 1, you'll end up with 0 equals 0. You know that's true, but it doesn't really get us anywhere. It just tells us that it's a dependent situation. So here's what we're going to do. We're going to solve for x in terms of z. So for instance, if I were to take this equation and solve it for x, negative x minus z equals negative 1, I'll get negative x equals z minus 1, moving the z to the other side. And then divide both sides by negative 1, or multiply by negative 1, depending on, what you feel like more. That's going to give me negative z plus 1. Okay. So I got negative z plus 1. That's part of my solution. That's going to be part of my solution, because that's going to be my x right there. So I'll circle that in blue. I got to figure out what's going on with y. So I'm going to take this and plug it back up here and solve for y. So let's do that. In fact, I'm going to do that on another sheet. I don't want to get too messy here so that we can't see what's going on. So I'm going to substitute x equal negative z plus 1 into x plus y minus z equals 0. So let's see what happens. That's going to be negative z plus 1. So I'm plugging it in for x, plus y minus z equals 0. Are we okay with that little substitution there? Let's combine the like terms and see what we get. So that's going to be, I'll move the y out front, y minus 2z plus 1 equals 0. And now, since I want to get y by itself, I can move everything else to the other side. When it changes sides, the minus 2z becomes a plus 2z, the plus 1 becomes a minus 1. And there's the other part of my solution. So I've got two parts now. Here's my x, here's my y. Problem is, I don't know what z is. This is what's called an underdetermined situation or underdetermined system of equations. I just don't have enough information to figure out what z is. If I had a value for z, then I could plug it in and get a value for x and a value for y. So my solution overall, instead of x, y, and z, I'm going to put this expression up here. So it's going to be, and I'll zoom out a little bit. It's going to be negative z plus 1, and then 2z minus 1, and I don't know what z is, so it's just z, like that. Now if you give me a value for z, well, then you can fill in the rest once you pick a value for z. But the equation of the line where these planes intersect, and it looks like this case right here on the right, the equation of that line is given parametrically by our solution right here. You can find any point on that line by plugging in a value of z.
Oh.
So that's what it's doing, is it's effectively tracing out that line. Now, WebAssign might ask for it in terms of t or some other letter. If it was in terms of t, that would be a t. What would this be? Well, instead of a z, I'm going to put a t. So it's going to be 2t minus 1. And how about the first one?
Negative t plus
Negative t plus
1.
1. So pay attention. In WebAssign, they might ask for it in terms of t as opposed to z. It's kind of going to depend on the whim of WebAssign. But you know, I don't know as I'll have a real preference on an exam for that one way or another. Okay. That one was hard. And because this is kind of new, I think we should practice one more like that one. And then I think maybe we'll set up system equations. Maybe we'll just solve it. We'll see. But let's move on, unless there's some specific question that you've got on this one. We're okay here? All right. So this one is example H, if you're following along with the handout. It's going to look like this. X minus 2y plus z equals 9. 2x minus 5y plus 6z is equal to 19. And 2x minus 3y minus 2z equals 17. Okay, let's see what happens with this one. And, you know, I keep on wanting to eliminate the z's, but then when I look at the numbers that I'm going to need, I become less anxious to do that. Because to eliminate the z from the second equation, what would I need to multiply the first equation by? I need to multiply by -6. That's just making my numbers a little bit bigger and messier. And it's a little more user-friendly to get rid of the x's here. So we'll stick with that. Let's get rid of the x here. I'll do that by multiplying this equation by -2 times row 1 added to row 2. Gives me -4x plus 4y minus 2z equals -18. Added to 2x minus 5y plus 6z equals 19. Okay, -2x. Oh, wait a minute. I screwed up someplace. Yeah, I was supposed to multiply this by -2. Rats. Let me try that again. -2 times row 1 added to row 2 should be -2x plus 4y. Yeah, I was just off here. Minus 2z equals -18. Sorry about that. 2x minus 5y plus 6z equals 19. Overall, I end up with -y plus 4z equals 1. Just leave that part there. Let's repeat this for the third equation. -2 times row 1 added to row 3 is going to be -2x plus 4y minus 2z equals -18. 2x minus 3y minus 2z equals 17 gives me y minus 4z equals -1. And that's what I was looking for. I was looking for 2 equations and 2 unknowns. So here and here, those 2 equations. So let's look at those two equations together. That's my 2x2 system that I need to finish solving. And I could solve this any way I want. Solve negative y plus 4z equals 1, and y minus 4z equals negative 1. What would you suggest in terms of solving here?
You can multiply one of them by negative one.
I'm not even sure you need to do that.
No, just hit the add.
Just add these two together, and well, wait a minute. I get 0 equals 0. Ugh. Zero equals 0. That's kind of a problem, right? I mean, all my variables dropped out. But that's telling you something. What's it telling you in this particular case? It's telling you you've got another dependent system. So let's just take one of these equations, and the second one looks the best. I can solve for y very easily just by moving the 4z to the other side. I get y equals 4z plus 1. So if y equals 4z plus 1, hey, that's great. Let me go back and see what I can do with that. I'm going to plug it into one of my other equations. In fact, the top one looks friendliest, so let me plug it in there. So, sub, minus 1, yeah, minus 1, thank you. 4z minus 1. So substitute into x minus 2y plus z equals 9. So basically I'm getting rid of the y here by doing that. And I get, let's see, x minus 2 times 4z minus 1 plus z equals 9. Okay, it's going to be x minus 8z plus 2 plus z equals 9. If I combine like terms on the left-hand side, I get x minus 7z plus 2 equals 9. Subtract 2 from both sides, I get x minus 7z equals 7. If I move this to the other side, I get x equals 7z plus 7. So I've got my solutions now. One of them is up here. Y equals 4z minus 1. And thanks for catching that. And the other one is down here. So as far as an ordered triple are concerned, x, y, and z, it's going to look like this. 7z plus 7. And for my y, 4z minus 1. And for z, it's just z. Just like that. Now, if you're asked to write it in terms of t, it'd be 7t plus 7, 4t minus 1, and t. Yay. And there you go. Whew. Those are tough. I won't deny it. Those will be the most challenging ones you're going to have in this section. So, comments or thoughts on that one? Should we practice one more where you have to solve it, just get a regular solution, or are you good on that part? Good on that part? Okay. Let me show you something that you're going to need to solve in the last, excuse me, in one of your problems at home. And that is, in addition to everything else, you get to set up the system of equations. So this talks about short-term, long-term, and intermediate-term bonds. So you can start out by giving these variable names. I don't know if you want to use S, I, and L, if you want to use A, B, and C, or X, Y, and Z. It doesn't really matter, just as long as you know what's what. So, any favorites? A, B, and C, X, Y, and Z?
X, Y, and Z sounds good.
X, Y, and Z. All right, let's keep it in our comfort zone. We'll do X, Y, and Z. X is our short-term bonds. Y is intermediate-term bonds, and then our long-term bonds. Short-term, intermediate term, and long-term. So it's not a bad idea to keep in mind what you're looking at here. And let's see if we can't come up with an equation. Mark has a total of $100,000 to invest. His financial consultant advises him to diversify his investments in 3 types: short, intermediate, and long term. So, okay, that actually gives you an equation. The amount of money you invest, X plus Y plus Z, has to be $100,000. So that's one equation. Let's see if we can't chase after another equation. The short-term bonds pay 5% interest, intermediate pays 6%, and long-terms pay 8% simple interest per year. Mark wants to realize a total annual income of 6.5% with equal amounts invested in short and intermediate term bonds. So if equal amounts are invested in short and intermediate term bonds, that actually gives you an equation. What that's saying is that X has to equal Y. Our short-term investments has to equal our intermediate term investments. So that's another equation. The last equation is going to come from the interest. So, oops. The short-term bonds pay 5%, intermediate pays 6%, and the long pay 8%. So when we add all the interest together, now the interest is calculated as 5% of the principal. So the principal is how much you're putting in each of these. So 5% of X plus 6% of Y plus 8% of Z has to give us income of 6.5%, 0.065 of our total. And our total was $100,000. So if you multiply that by 0.065, 1, 2, 3, 1, 2, 3, I think you should be getting 6,500. My brain's a little addled. I just want to make sure. 0.065 times 100,000. Yeah, 6,500. So this equation really could be set equal to 6,500. And there's your 2 equations, or 3 equations, 1, 2, and 3. Now I'll show you kind of a nice way we can attack this problem when we get to section 10.3. But here's where we're going to leave it rest for now.